You want to okay?
Yes.
Okay, we get started.
Sure.
All right, sorry for the slightly late start. Welcome back, everyone, to the CSE Seminar. It's an absolute delight and pleasure to be hosting John Azariah from Microsoft and Brisbane. He's come all the way from Australia just a few days ago, hopefully recovered from his jet lag. He is one of the original authors of the Q# programming language, has a variety of interests ranging from functional programming to cloud to all kinds of fancy things. I have a very limited understanding of, so I will not even try to elaborate. And today he's going to teach us the questions. So it's all yours.
Thank you. It's an absolute privilege to be here in front of you. I see a few friendly faces that I met already. I hope any of this stuff, please, it's an intimate little gathering, so please feel free to stop me halfway in between. In fact, out of respect for the whole, I'm talking to a bunch of IIT people, I dispensed with the PowerPoint presentation. I figured we'd just talk code, right? Now, how many of you people have actually done anything with recursion any time? Right, everybody. How many people like it and feel like you understand it?
Understand it is different. I like it.
Right. So in the industry, there is possibly a marginally arguable stance that recursion is a dangerous tool. You don't want to use it because it's quote unquote inefficient, possibly will blow your stack. And you don't want to do that. In fact, for efficiency reasons, if you ever try to join Facebook or Netflix or one of these guys, they'll give you some kind of dynamic programming problem, which from lead code, which involves you having to do some significant amount of computation, which frankly, if you could use recursion, would only be 4 lines of code, and there wouldn't be any mystery to this whole thing, right? But clearly, specifically because it's complicated to write the iterative solution, that's why it's an interview question, right? And so some of the things that we talk about, what is the inefficiencies? Where is the source of the inefficiency? Where is the source of the misunderstanding and so on? That is kind of what I want to cover today. So we'll start with some basic things. There's a section in here that I can add on later, or we can talk about after this if you want, that actually has the mathematical underpinnings of the lambda calculus and stuff like that. But none of that's actually needed for actually understanding how we can build up principles of recursion from literally nothing other than function application. Okay, so everybody knows what factorial, right? And so my friend, our common friend, Sriram Krishnamurthy, who's here for a while, respected teacher of computer science, hates the fact that anytime you introduce recursion, we use factorial. And like, who the hell actually relates to factorial? What does 9 factorial mean to you? Nothing, right? You can't even like conceptualize what it is. I guess unless you do traveling salesman problem, then you have an idea that factorial is kind of important. It's a big number and so on. But I'm going to actually go against his advice. I'm picking factorial simply because all you guys actually have encountered the problem before, right? So this language is called F#, and I'm going to execute that code, and it gave me 10 factorial. And F# is sort of a variant of OCaml. It's a functional programming language. And one of the cool things about F# is you have to declare all your functions before you can use them. But with a recursive function, the declaration uses the function already. So you have a problem. You can't actually use standard complete forward without forward declaration. You cannot actually have a recursive function. So you have this little magic keyword in here, which you have to put in saying, hey, hang on, I'm about to tell you what fact is. It's in terms of what fact is, right? If I take the rect out, It'll say, I don't know what you're talking about because you haven't defined fact, and I can't define fact without defining fact, right? So you'll find a few jokes of this nature, recursive jokes of this nature throughout this talk. If you feel like groaning, go ahead. So what we're going to do instead now, instead of saying, let's take out recursion from the language, we don't want to use that at all. What we'll do is we'll say, hey, I'll give you a function. And anytime you want to call that function. Now there's no problem with that forward declaration. In this particular case, omega is a function argument. It's an argument, takes integer, it returns an integer. And this f is defined in terms of omega, but omega is an argument. So there's no problem with defining it like this, right? But of course, I can run that. And that says, hey, if you give me an omega, which is of type int to int, I will give you a function that is also of type int to int. In factorial is that kind of function, right? But so what do we pass omega with now? What should be the initial pass of omega? Well, let's just take any random function, right? Let's create the worst function possible. Whatever argument you give me, I'm going to blow up. I'm going to take that function, and I'm going to call that function. And this thing, I'm going to claim computes the factorial of 0 correctly. Okay? It does. Factorial of 0 is 1. Now, why does that work? It works because I'm going to give it a poison pill. Error is now this poison function, but I'm going to pass it in as omega. But in this match, 0 matches to 1, so the poison function never gets called. You don't have to actually why. You can pass in anything you want, and 0 factorial will work correctly. If I pass, in fact, 0 of 1, then this thing will actually explode, which is expected. That's what's going to happen. It's going to call the error function, and the error function is going to blow up, right? So what's another function that has the same signature of int to int? Well, fact 0 is a function that has the same signature. So why don't I pass fact 0 into f and create this fact 0 function? And I claim that this will compute the factorial of 1 correctly. And if you think about why that works, it's because the first time it calls the match function, it's in the case of 1 and says, okay, I'm going to call whatever omega you gave me. The omega is fact 0. The next time around, fact 0's match function says, I'm being called with 0. I don't have to blow up. So the blow up function doesn't happen. Whereas if I put fact 1 of 2, this will actually blow up. This is to be expected, right? And we can do this again. Let's take fact 2 and put this. I claim that it will compute fact 2 of 2 correctly. And indeed it is. It's 2. So I'm not just returning 1, right? Like it's actually slowly computing the factorial. It's just a bit annoying that every time I want to create the factorial of n, I have to now define the factorial of n minus 1 and then all the way down. And that's kind of like the recursive definition of factorial, but I don't want to sit here and write all that code, right? So I'm kind of getting there. What's really happening is if you expand the thing out, it's like this. Because the fact 0 is on the inside, fact 1 is the one rounded, fact 2 is the one rounded, fact 3 is the one rounded. And so if you repeatedly apply f to this whatever omega function I give, I can get factorial of n. As long as there are n applications of f, I'll get factorial of n. So now our problem is reduced to actually figuring out how to type so many f's in that expression. And then we can go home. So for factorial 50, I can create one expression that has 50 f's in there. And that will calculate anything up to the factorial 50. And that will be the end of the lecture. You guys satisfied with that explanation? No.
Not with the end of the
No. Okay. Good.
So what's the type of the error function again? It takes an integer
And blows up. So it's actually technically from a functional programming perspective, it is not a total function. Okay, a total function takes all values from the domain, gives you some corresponding value in the range. An exception says, I don't have any value in the range, I'm literally going to blow up. I'm going to throw an exception. So in this case,
So any input error gives you an exception. That's
yeah. I've just said error. Pass whatever x is. The only use of x is to tell you that x went boop. That's it.
Is X even an int? I mean, not that it's relevant, but
It turns out that because this is quite a sophisticated programming language, that you have something known as Hindley-Milner type inference. And what that is it's just like Python, except types A, right? You define the function, it says, oh, there must be a type A. It gives me back some result of type B. But when I call it, it says, so I called it with int. So A must be int, and I get back a result of something. So B must be that result. So in this particular case, it's really A to void, which then gets invoked everywhere as int to void. Okay. All right.
the wrapper functions are int to int union point.
I want int to int, but it's actually int to exception, which is not really a type signature, right? But so fact 0 is int to int, and you can pass that into f, just like you passed error into f. And fact 1 is also int to int, and you can pass that into f, just like you pass error into f. So we kind of do the same thing. They all look the same in terms of the shape. So let's go back to this expression for a second. Yeah. So we take a look at this fact 0 thing. What that is, as we expand it out, is f of error with 0. And if you expand f out, it's this function, right? Which basically took an omega and called that omega, right? And just going back to where we started. So this is the initial expression of what f was. And the first argument f is error. And this would then give me a function which took an int to an int. And I'm giving it 0 for that int. So that's what that expression is. So if I look at this is actually the same as factorial of 0. All right. Now, what we'll do is we'll wrap this with a function that just calls the function, right? And that means omega is the argument to that function. Error is the argument to the result of that function, which is the same as that. And 0 is the argument to the result function, which is the factorial that we want to compute. Okay? So it's just mechanical. I'm just putting a wrapper around it, and I'm calling the wrapper immediately.
I have a bit of trouble understanding what you're saying.
Okay. So let's say we had this expression, right? So what is that expression there? It says there is a function which takes an argument. The argument to that function is omega. The value of that argument is error, right? That's going to return me the factorial function of 0, that fact 0 function. And I can pass 0 in as an argument to that. So that's fact 0, and we're done, right? So what I've done is I've just taken another identity from argument on top and said, I'm going to pass you something here. Whenever I pass you that, call it. And so the thing I'm going to call is, I'm going to pass it in this function. So this is exactly the same as that. All I've done is I added one wrapper around it, which gets called immediately. No, it's x is, well, the return value of a function is the evaluated function, right? So in this particular case, you're actually going to call omega.
The outermost wrapper looks like an identity function, x to x.
Yeah, but that's what it is. So the x of, so if I look at this side, if you use one way of looking at it. So if I look at this expression, the identity function with that expression is that expression. That's what's happening here. So I just put an identity on the top and passed in this thing. So the result of this thing is the same as that. Okay, there's a reason for that. I'm going to say, okay, instead of just returning the identity, whatever I give you, call it with error. So then I promoted this argument from down there to up here. So now if I pass in this function, it will call it with error. You return a function that takes an integer. That's the integer. It should compute 1. And indeed, it will. Why am I doing this? Because if I do 1, it will blow up. It's the same function. Here, I can now start repeatedly applying x. Just like we wanted to apply f a bunch of times, here I can repeatedly apply x. So now if I have 50 here, 50 x's, this expression will work up to 50 factorial. Got it? Okay. That's the end of the talk. No, okay.
You have to do still, like, you don't want to type X a lot.
You don't want to type x a lot. How many times should I type x?
Preferably once.
Twice. So there's a reason why I'm going to switch to JavaScript now. So I'm going to switch to JavaScript, which is going to be interesting because I don't know whether the Zoom people are going to see this. Yeah, I might have to do.
Used to the pause notation.
Yeah, there is a little bit of that, but let me show you this. How about I just share the screen? Yeah, let's do that. The Zoom people able to see what I'm doing?
Yes,
Yes, we see your desktop.
Excellent. Okay, so here what I'm going to do, I'm going to go in here and create in JavaScript something that takes x, a function, and it calls itself. Right? So give it x, it calls itself with itself. And if I hit the enter, nothing should really happen. It says, this is an expression. I don't really know what to do with it. It just looks a bit funny, but it's an expression. Now, I can take that expression and call it with itself. So let's do that. Let's just say h equals x to x of x, right? And then I'll call h with h. So what's happening here? I've got this function. I'm going to pass itself as the value of x. What do you think will happen? What's the intuitive thing that you're seeing is going to happen? It's going to call itself over and over and over and over and over again, and then die like that. Right? That's a Stack Overflow. So we found a way now to call something by itself over and over and over again. We don't write it out 50 times. We can actually generate that infinite sequence in there. Now, the problem with this is JavaScript tries to eagerly evaluate anything. That's why it's blowing up. So I want to do something interesting with this. What I'll do instead is, yes, absolutely. So how about that? Is it good? Okay. So here what I'm going to do is I take a little function, and more importantly, this thing is Stack Overflowing, right? So I'm going to take a function. I'm going to give it, this thing keeps calling x, but that is of no use to me. I want to be able to do something useful every time it calls x. So one interesting thing to do when you want to call x a bunch of times is call an f function whenever this iteration happens, right? So what I'll do is I'll pass the f in. Which f do you want to call? I don't know. Pass the f in, right? So here what I'll do is I'll pass the f in to the same expression and call f every time. Right? So it's the same as this, except that instead of the x to xx, I'll pass in also an f and exercise the f every time that iteration goes through. Now you'll have an infinite number of calls to f. In addition to the Stack Overflow, you're going to have an infinite number of calls to the f as it goes out. And that's actually kind of interesting. So if I do that, it says, yeah, okay, you've given me a function, it takes an f, and there's this expression over here. Let me call that something. Let's call that z, because, there's a dead giveaway there. And now So what does Z want? Z wants a function, right? Which is going to get called over and over again, because the argument that I need to pass in here is the function that I want executed. So I pass in some G, and it should actually work. Now, before I do that, I want to just walk through the maths with you. So here's what that looks like. So Z of G means you'll get this expression, right? G, because I gave it F gets replaced. Z of G means I'm now taking the G and fulfilling this argument. So I just plug it in over here, right? And this expression is a function, right? So if I take this bit and plug it into this X, because that's what I'm doing. You have a function, you have an argument that follows, you're now going to apply this. What will happen is you will get back this expression, because if I take this value and pass it in as the formal value of this X, you will get G of wherever X is, this expression, G of X to G of XX, calling X to G of XX. You follow? So when you do the application just textually, that's all that we're doing here. This is actually all the foundations of function application is. When you've given an argument to a function, take away the parameter, replace all instances of parameter with the argument value. We're doing exactly that here. But what's cool about that is you get back Z of G to start with. So Z of G is the same as G of Z of G. So those mathematicians among you over here now realize that the Z is actually the fixed point of that G. Whatever you pass in, this Z of G returns a fixed point value. So you can apply it many times, you'll get back the same value, right? So Z of G is the same as this, which is the same as G of Z of G, which is the same as G of Z of G, and so on. And now we have a way of invoking some G n number of times with a simple expression. Still an infinite number of times, but this is a lot better than having to type it 50 times. You agree? Okay. So what we'll do is we'll do exactly that. We'll take this value and stick it into F sharp. And F sharp will actually complain because it says, hey, your types don't line up. JavaScript is fine with any of this stuff because JavaScript says, you're passing me some object, I'll treat it like whatever it's supposed to be. If it's treated like an integer, I'll treat it like an integer. If it's treated like a function, I'll call it like a function, right? But F sharp says, no, you have to be explicit about what type things are. So you have to do some type magic to make this happen. I won't bore you with the type magic, but really what we're doing here is treating X as untyped, which slowly relaxes the problems that we face with it until you get to this. So this is the incantation that you mumble in F sharp, which is equivalent to that Z of G thing. It's just that you have to put in this type hint over there, and then you have to do this type cast over here. And at the end of it, you get something which drives this function infinite number of times. Except that it doesn't drive it infinite number of times, this function terminates. And because this function terminates, this sequence will terminate when this thing terminates. Because you keep calling F, right? You keep calling that F function. And the F function basically says, I'm done. And then your infinite calls to that Z will stop at that point, right? So now we can actually try to see if we can run 10 factorial, and we can, right? So what have we actually achieved out of this? We have actually split up a bunch of concerns. Between lines 148 and 152 over here, we have the thing that we want to repeat. We want to repeat that n times, right? And that's going to compose itself into a value, which is recursively computed. We got something here that drives this value.
Sorry, I didn't have a complaint here about P being in mode.
Which one?
So in the thing that you want repeated inside, function P is n times P of n minus 1.
Yeah.
P is the variable.
So,
that was same as the omega.
yeah, this is the omega. I just put omega in here and that's the end of that, right? So this thing drives this omega function, right? And this bit over here is the driver. So this thing closes the top. This is the argument to that. So the f here is this function that gets called every time we run it. Okay? And then we can run it until this P stops. So this gives us almost everything that we want, right? It gives us the recursion that we started out with because we had that omega function that we had to compute one step at a time. We have some mechanism here which generates an infinite number of calls to drive that. And the termination is provided by this thing just like we expected it to. So if you look back at the initial factorial function, it said, hey, if it's 0, return 1. Otherwise, recursively call myself. That's actually what's happening here. But the recursion is now explicit in that f call. Right? So now that we've got that,
Also like apply the same recursion algorithm, like abstract, where you can apply to different functions at different order.
Right. If this was my class, you'd be getting an A by now. Because this is the whole thrust of the conversation. Because when you do this thing.
To be fair, I studied a bit about Church numerals ahead of time.
Oh, great. So you basically came in prepared for the talk.
No, it was by coincidence. I studied Church numerals while reading SIC.
Good. So here, if you look at this function over here, is actually that combinator. It's the lazy version of what is known as the Y combinator, because it allows you to eagerly evaluate stuff. Everything here is delayed enough for you to be able to only run the recursion when you need to run the recursion. So this bit is the Z combinator. And this Z combinator now allows you to hoist any single step recursion step and make it fully recursive. It generates the recursion part of the thing. Now, why is that kind of useful? Well, so we've already done this factorial gen thing. We can run this. This is the same as the Z of factorial gen. We're good to go. And now we can start getting really interesting. Now, remember that first factorial function? If you want to actually trace what happened in that factorial function, you're going to open up the code of that function and make the change in there. Right? You're not actually composing behavior. You're actually injecting the thing in by editing the stuff. Right? And you guys are thinking, I do that all the time in Python. Well, guess what? You have no choice but to do that in Python. In this fine functional programming, you really want to just compose the two things. So there's two pieces. One does the factorial computation, one does logging. The two independent constraints, you want to just log them together. So if I create this log thing, and I create a loggable version of factorial gen by just composing those two functions together, then I can run this and it will log it.
What's the double asterisk? Sorry, double.
This is the composition. So this says take these two and compose them and make one function out of it. So it's like given f and g, it gives you g of f.
So it's a primitive.
It's an operator that you can use, but really what this is this is the composed version of factgen and log. Factgen has no logging in it, it's got its own function. Logging doesn't care about whether you're running factorial or something else. It's composed those two functionalities together, returned a function that you give to Z, and Z went and did this. So now all of a sudden.
Sorry, can you also write log of factors?
Yes, you can do either. It doesn't matter whichever way you do it. It doesn't matter at all because
And
this function is going to get called every time the iteration takes place.
But it means that a function which takes a function is input is function optimization, right?
Yes,
So log can take action as input instead of.
yeah, but that's the same as this. That's what this does.
Notation is.
Yeah,
so the
that's
composition is log of factor, right?
yes. Right? Now let's play with it a little bit more, right? So let's forget about factorial for a moment. It turns out that this is actually quite efficient. If I do this thing, I can actually get the 200. I can get like so this is the log, and then I can basically say I can get 200 factorial, which is quite a large number, right? So I'm not just fooling around. I can basically do quite a bit of interesting stuff with this thing. Similarly, here's Fibonacci. Now we know this Fibonacci expression is pretty trivial. 0 goes to 1, 1 goes to 1. Otherwise, it's 2 Fibonacci's added. And if I try this one, what do you expect will happen? What do you think will happen?
I mean, it will call Fibonacci multiple times.
Correct. Now, how many times will you call Fibonacci for 10? You call Fibonacci of 10 is 9 and 8. 9 will call 8 and
It will call
7.
it a log because it grows exponentially as you.
Okay, so what is the cool thing that we want to do with that? We want to remember that we've already seen something and then use the seen value. Otherwise,
So we don't calculate the same value twice.
we don't calculate the same value twice. We want to do that. But we don't want to write anything in that nice little Fibonacci function. This Fibonacci function is clean. I don't want to be mucking around by saying, put an if statement in there. That's not in the Fibonacci algorithm. Right? So what I do is I create this little function, which is called memoize, which is a classic term for saying, hey, get me a value from whatever memory you have, or compute it and put it in the memory so that when I ask you for it again, I'll give it to you, right? So this is this piece. And this memoizes any function that goes from A to B with a dictionary that goes from A to B. Okay, this is about as close to mathematics as you can get, because really what is a function in mathematics? It is a map between domain and range. That's what that is, right? So here we are. So if I memoize that now, set memoize to be whatever that is, create this. I'm still complaining about, let's hold this for a moment. This should actually compute the Fibonacci of 50, and it'll compute it. Just give me a second. I want to find out why it's complaining. So why is I wonder why. I think there's a typo in here somewhere. Let's keep this for a moment, okay? So what I've done now is I've taken it to the next step. I've created a new kind of, so you remember that Z thing was a kind of combinator that took something to something else? I'm going to create a nice big combinator. I'm going to call it RM. That's the same as Z. I've taken it out from there. That's the same as M, memoize. Here's log. And here's something that does the timing and then calls the function and gives me back a proper result, right? So this is a fairly sophisticated combinator that basically wraps the combinator, the Z combinator, with a whole bunch of stuff, including memoizing and logging and all this other stuff. And let's just take this Catalan function, which if you go back and look at Wikipedia, if you don't know what Catalan is, is a fairly sophisticated recursive function that's written very neatly. It's a form of a sigma that you basically have to sum over the previous n Catalan numbers to give you the value if its n is not 0 or 1, right? So it's quite a complicated thing. Now, if you normally had to do this Catalan function, you would use dynamic programming. You would have some way of actually turning a problem inside out and saying, I know how to compute Catalan of 0 or 1. And now I'll compute Catalan of 2 because I know those two values. And then I compute Catalan of 3 because I know the next two values, and so on and so forth, all the way down, right? But that's not how Catalan is defined. Catalan is defined like this, top down. If it's 0 or 1, maps to 1. Otherwise, sum all the previous n minus 1 terms. So to compute n, you assume that you already know the last n minus 1 terms, and you figure out how to do that. The fact that you haven't computed those previous terms is actually not a part of the definition of Catalan. Just assumes that if you just sum the thing, it should work. So let's do that. Let's not turn the problem inside out. Let's not try to make it bottom up. Let's take the expression the way it was and run it, and you get the result. The result of Catalan 10 is 16,796. And it did that with 11 calls, which is exactly what you expect. To compute Catalan of 10, you need to make the computation of 10 to 0. 11 numbers you need to compute. I've computed only 11 numbers. That's what that whole keeping track of how many times I counted gives us. So we didn't do any wastage. We didn't do any recomputation. We didn't do any of that inefficiency that is normally associated with this recursive thing that requires you to go into dynamic programming and like use, a top-down memoized approach or whatever it is. You can take any old recursive function, stick memoization in there, and the stuff will work.
And these 11 recursive calls, the last one is still sitting on top of the 10 that's stack.
The stack size, you're absolutely right. In this case, the stack size still stays linear. Okay? We can fix that. Not now, not in this talk, but there is a technique, and if you want to look it up, if you guys are interested in looking it up further, there's a technique called using trampolines. And if you look at trampolines and Y Combinator, there are a bunch of articles that actually compute a recursive call with a constant size stack using this trampolining method. Okay? So let's come back to Fibonacci. And we have this problem, and it's computed the first 10 Fibonacci numbers. And again, you'll see that the cache size is one more than what the input was, which is exactly what you'd expect, right? And you can see that it's flying along. Like you can actually see that it's not slow. So,
How you calculate the cache size?
okay, so let's go back to this. I'll tell you how the cache size is done. So if I go in here, there's a memoized function. If I want it to be verbose, it'll tell me. And then when I get the result back, it counts how many items are there in the map, because that's how many times I put something in there. And the only way you put something in the map is when you make that call. Because otherwise there's no way to put the value into the map, right? So I'll finish with the Levenstein distance, which is again a classic problem in dynamic programming, right? And if you had to write out the non-recursive Levenstein implementation, it is a complex enough problem that it has some score on lead code that is not trivial. It's non-trivial problem to solve. You have to come up with the iterative solution for it. And in reality, what you need is the mechanics of well, first of all, there's a mathematical foundation to this. There's a well understood mechanics for actually generating the recursion part of it. And then there's ways to control that recursion by giving you the ability to log the information, memorize the value, do all of these other things. So by putting all these together, that's the real way you want to compose up a solution. You can actually compute the Levenshtein distance in 6 lines of code because the definition of the problem is only 6 lines of code, right? And if you look at the answers to these, it will tell you that the distance between sunny and snowy is 3, and the difference between kitten and sitting is 3. That's what you expect. And you get the right answer without having to go through any of the rigmarole of turning things inside out. So this should give you an idea that recursion is actually a functional construct that's not dependent on the language. Even in languages that have only function application, you can generate recursion. Okay, so that's the first takeaway. Second takeaway is the recursion that you get from this Y or Z combinator approach gives you fine-grained control into each iterative call, something that you don't actually have in a standard recursive function, little language. Because any fine-grained control you want for the inner invocation has to now be baked into the definition of the function, which is actually not a very nice thing to do.
Could you elaborate on what you meant by the recursive thing doesn't depend on the language or didn't understand?
Okay, so that's a great question. I'll finish with the third and final takeaway from this, and then I'll come back to your question. Yeah. So the third thing is, because you have fine-grained control, you can leverage memorization and actually use that to build very reasonable, elegant solutions that would traditionally, using other approaches like dynamic programming, be convoluted, complex, and basically more difficult to write, difficult to comprehend, difficult to understand. All right. Now, is this the most efficient way of doing it? No. You'll always have a situation where there's a hand-coded mechanism that unrolls the recursion or optimizes what you actually do at each step because you're taking specific knowledge of the problem and leveraging that. This doesn't do any of that. The Z combinator doesn't actually care what you're using to recur, what you want to recur on. It could be recurring Fibonacci, could be recurring factorial, could be recurring anything. The Z combinator just works, right? So there's a trade-off. Is there a trade-off? Yes. The trade-off is this. If you don't take specific advantage of some knowledge of the problem and you're willing to basically complicate the code, you will get a better solution. But if you want a general, clean first cut that is provably correct, so there's fewer chances of bugs entering this mechanism because the recursive mechanism that does the iterative part takes care of itself. It's not something you write. You can come from a library. You're only focused on writing that recursive bit. So if you want to find a bug in your Levenshtein code, the bug is in those 6 lines, not in the 65 lines that you wrote in the iterative fashion, right? So that's actually how this stuff benefits you, right? So I'll end the talk there, I'll answer your question, and then I'll point you to the fact that if you want to go further into this, there is actually the lambda calculus that you can look at, where you can actually derive, very much like how I've done. I've kind of empirically sort of walked through the steps of how to create this combinator. But there's a formal definition, like Azariah put it in. There's a paper that you can go and read. There's a formal definition of how to create this Y combinator and some of the properties of it. All right? That's the talk. Now your question. Let's go back to the very, very first part of the page here. So you see, when I told you This is in Python. In Python, you can simply define a function and call it inside the definition of the function, right? And Python says, okay, I'm defining a function. I'm going to call some function called something. And nothing happens until you actually invoke the thing first. Because then it interprets, it says, I need to call this, so, that's that function. So then it calls itself kind of blindly. With a type-safe language, and especially with type-safe language like F#, where you have no forward declaration, you can't use fact without defining fact, right? So if I didn't have language for specific language support for recursion, this function won't even compile. It will say, hey, I don't know what you're talking about. You're asking for fact here. I don't know what you're talking about. I don't exist. This function doesn't exist. The function doesn't exist because it's being defined in the function that's calling it, right? So therefore, you need language support like forward lookups to be able to do that. But the rest of the talk didn't use that support at all. We just passed in our omegas and we did jiggery-pokery with that to basically generate that infinite sequence of calls. And we did all of that by just depending on function application. Was it a bit ugly in the middle? Sure, for the same reason. You have some X, you want to call X with X, and the compiler is confused. It's like, hey, what are you telling me, right? They're passing me something and then you're calling me with that something. What should that signature on that something be? And you have to loosen your type restrictions in order to get around that. If you did this in JavaScript, you won't have any problem at all. If you're doing a tightly, strongly typed language, you have to go through this type gymnastics stuff to make it work. So you see here, if I just took the same thing that came from JavaScript and did that, it would say I have a type mismatch. So if I cast it saying, hey, I'm an object that returns something, right? So you can call myself with myself. Then the next invocation is it gets confused by. So if you do a little bit of this type like gymnastics, then it accepts the thing and it works, right? Because that's really what you're doing. You're freeing it from the type algebra, because you know that until it's in the terminal case, you're always passing in a function. And at some point, you'll have to pass in a terminal case. So this thing is schizophrenic. It's either an object that you pass in or a function that you call. So one of those two things, it has to be both. And the type system with the strongly typed language doesn't give you the flexibility to do that without you hand-holding it and saying, hey, treat me like an object if you need me to be an object, which is kind of what that is. All right, that's the talk. Any other questions?
Nice question, but with the left back,
Hmm.
if you drop the base case, does the linter compute?
Oh, it won't complain that it's infinitely recursive. No, and the newer versions of F# basically allow you to say, hey, really what I mean is, I mean to define a tail recursive language, because F# has tail call optimization. And that's a cool way of actually, if your function is tail recursive, then it can be computed with constant depth, constant stack depth, right? It turns it into a for loop, basically, right? So there's benefit to making your function tail recursive, but we are just totally naive. We take the definition of factorial from whatever ancient literature somebody scrawled on and use that. And that's not tail recursive. So there's an annotation that will complain if you say, I want it to be tail recursive and it's not, but there's nothing that prevents it from being infinitely recursive. You'll just die. There's nothing in the type system that can even possibly tell you that that's the case. Anyone else? Anyone online? I think they've all left.
successful.
All right. And that's it for the talk. Thank you.
I mean, you mentioned reading stuff on reading up on lambda calculus, right? So would you be able to say like, well, I've written that, how exactly on what places to read?
Okay, I should before I actually stop the recording of this thing, I should acknowledge that this talk was deeply influenced by a talk by a fellow called Jim Wyridge. Jim Wyridge, who was a leader in the Ruby community and who died actually 10 years ago, 2 days ago. So he died just over 10 years ago recently. He had a beautiful talk explaining the Y combinator. Okay, and he goes through the excursion. I tried to keep this to under 45 minutes. I don't know whether I succeeded or not. He goes through an excursion where he talks about how the lambda calculus would actually work, right? And there are three operations and like three things, properties of lambda calculus, and those three rules are the only things that you need, right? To even generate this 6-point combinator thing out of it. There'll be a link, I can share a link to the talk with you, but if you look up Jim Wyridge Y combinator on YouTube, you'll probably get it. Hit me up if you need me to.
And also about the thing of programming language, like you mentioned that we sort of did a workaround around the type safe thing, defining recursion another way. I wanted to ask, doesn't it also depend on the, let's say, degree of freedom that a programming language allows functions? Like, can functions be even returned functions can even be returned?
Absolutely, you're absolutely right.
It depends on the degree of this. Usually, I won't say usually, but like if you're telling to growing from C++ background like that, the degree of freedom of variables, like assigned variables, is a lot more, and you don't return functions, you return pointers to functions.
Yeah.
Right? So does that? So it also would depend on that, right?
To some degree, I think pointers to functions is still not a problem. They're the same thing. The problem is constructing the pointer to the function that you want and returning that. Language. So in languages that actually support first-class functions, there's a spectrum of stuff that's dead easy, like Haskell and Lisp and F#, to stuff that's dead complicated, like C++, right? So they all support the same semantic of first-class functions. Some have less ceremony around it than others, okay? For languages that don't support first-class functions, there's a hierarchy as well. There's a spectrum. If you can't use functions as first-class objects, none of this stuff will work, right? In those functions that support functions as first-class objects, you have untyped languages like Lisp and JavaScript and even Python and so on, which are sort of easy to work with in terms of this lambda calculus stuff. On the other side, there's the type angle, and then there's the syntactic sugar angle, where you can't really return a function, you're returning a pointer to a function, so you have to create the pointer to the function itself, and then return that. So constructing that requires more ceremony. You have to stand on left leg and wave a dead chicken or something. That kind of thing. It all depends on like the language that you use, but the fundamental piece that you need is first-class functions. Any other questions? Can I stop the stream? Sure. All right.
I have a question.
Yeah.
So how does it help in, recursive functions like the Fibonacci series?
That's a good question. So the expression of the Fibonacci series is a lot simpler if you just follow the classical notation of Fibonacci series being the nth term being represented in terms of the n-1 term and the n-2 term, right? So instead of having to somehow obfuscate that relationship by, in the name of optimization, you can actually use the naive the naive representation of the expression. Okay, so that's the first problem, first benefit. The second benefit is that Fibonacci is actually exponential in time if you don't memorize, right? At the cost of linear amount of space, if you take that, if you don't give that linear amount of space to memorize the functions, then you land up with an extremely long call time, right? And so this approach allows you to take the naive representation of the Fibonacci expression, compose it with the ability to memorize that function, and basically get back runtime at the expense of linear space. All right, that's what this gives you. It's not the most efficient implementation of Fibonacci because you can further go back and say, hey, hang on, I don't actually need linear amounts of space. I need constant space. I only need to remember the last two terms, right? So you can even tweak, you could tweak the memorize function to keep the last two calls, or kill, it's sort of an LRU cache instead of a standard dictionary. That'll give you that ability back. Or you basically turn the problem inside out, rewrite everything on paper, draw out the call structure, and then say, hey, I only need the extra variable and I keep swapping the values and get the Fibonacci number that way. A la any job interview question kind of thing, right? This doesn't take you all that way, but it takes you a heck of a long way there. Does it answer the question?
Yes, thank you.
Sir,
Yes.
You are using checking the type and checking that function is returning the right type. So you are doing it before the last call, where the time will go wrong. You are let's say you are invoking the error function first.
Yes.
Then you are calling then you are calling the function.
So we try not to call the error function at all. So I gave you the example with the error function and showed you that if you use the error function, it will only get called if you have the wrong number of invocations. So if you give it an argument,
it will give different output.
Yeah, you basically blow up if you have the wrong number of calls.
Maybe like a Bob timer, right?
Yeah.
Maybe like avoid getting there.
It's like going there and then seeing that if we reach some value.
It's like a baby that can only count to 3.
Yeah.
That's right. And if you give it 4, it basically chokes at the last stage.
It's like only at one number it is.
Right. Right.
So I want to it saves the calls if
you want to save all the calls.
I know you are saving the if else conditions that we put there and
yes.
And you are doing not necessary conditions where we are actually before that we are actually
you're exiting, and the reason why you exit is because that step that you're using to be called multiple times.
At last you are not actually calling this.
That better terminate. If it doesn't, there is that Z combinator is perfectly capable of generating an infinite sequence. So it's going to generate an infinite sequence until you terminate. If you don't terminate, it's going to keep going until the stack overflow.
And if there's a recursion you are released, you will have those calls and you are not actually calling all those calls. You can actually do your checking that the error type is actually correct.
The type checking happens before anything runs. No, it happens before anything even compiles. It's happening while it's compiling. So nothing will run until the type change.
Yeah, but type changes well.
No, in this particular case, we're casting up and down, but we're casting between two things. Either it's a value or a function, and you're casting between those two to do the right thing. And you only invoke it when it's a function. So it's casting the type. It's not really checking it. It's basically coercing it, saying, hey, really what you passed me you said was an object, it's really a function, call this function with this value, right? And if that cast fails, for whatever reason, then the whole thing will have runtime error and fail. But you know that it can't fail because the value that you passed in was a function. You're passing in a function, so you can treat it like a function.
Yeah, it's more efficient. You are not.
Oh, it's definitely, well, there is I mean, the casting part has an implicit if else in there,
But
it's built into the system. You can't get out of it.
If you're getting at what is the point of doing it this way, in terms of what if anything of it, at least the way I saw it is that it's a puzzle where, let's say, I don't allow you to use a function if you're not defined it yet. Under this constraint, how will you implement recursion? And I think this was breaking it into two parts. One was saying that you can trigger this infinite recursion without any problems.
yeah, you go down.
Then you separately have this thing which pushes the brakes and says that they call it exponents. And you put these two pieces together and you have this magical thing which is an implementation of a recursive function without ever having to be in a situation where you're calling the function before.
Right. The Z combinator is a function that generates an infinite sequence. So a Z combinator is a function that takes a function f and calls f an infinite number of times automatically.
And you plug in the
And then you pass in the right thing for f,
so
which will terminate at the right time.
So you are like playing with types.
Yes, to some degree, yeah.
Yeah, so if you want to do that.
Any other questions? Cool. Thank you.